So the thing is that, when we look at a wave packet like this, right? So it can be, it doesn't have to be exactly like this, but, and it's going along merrily in its, it's traveling in that direction. And with time, this will spread out. Okay, in time, this will spread out. And that's because, if I do a Fourier transform, we will see that it's consisting of different, momenta, and different momenta will have different speed, and therefore their linear combination will change with time. So it'll spread out because there's a whole range of phase velocities here. But as long as the potential energy is not changing, the group velocity of this wave will not change, and that will be the velocity of the particle in the classical limit. Okay, and we can express this interesting fact by Fourier transform. Now, now we come back to physical observables. Okay, what are the physical observables we can measure? So, we are given, I said something like psi, the wave function has all the, physical information. About the state of the system, right? And I also said that psi squared is the probability density, right? And that was called the Born interpretation. So you can ask, okay, where can I find, I can ask physical questions now, like, where can I find the particle? Okay, so you ask that question. So, it's a vague question, and as a physicist, I interpret it by saying that what is the average value of the position, right? Would you agree that's a good interpretation of this question?
Yes, sir.
Okay. So in one dimension, we have to find the average value of x. X is the position of the particle. Now we go to probability theory. Now in probability theory, suppose we have a random variable x, then the expectation value of some function of that random variable, so it has some, okay, so the random variable has some probability distribution, right, p of x. So the expectation value of some function of the random variable will be given by f of xi, p of xi. Xi are the possible values. I do a sum over all the xi divided by this thing, right? So this is what I called the expectation value of the function of the random variable x. Okay, so this is what we call an average. Are you familiar with this definition of average?
Yes, sir. Yes, sir.
Okay. So now what we're saying is that suppose I have some, some function of x. X is the position of my particle, quantum particle. Then what is the expectation value of f? Then according to the Born interpretation, it should be, I should integrate it from minus infinity to plus infinity of that function weighted by psi of x of t squared according to Born, d of x divided by the normalization in case we have to normalize our wave function to be unity. Okay, right? Do you agree? This is the expectation value.
Yes, sir.
Yes, sir.
Yes,
So does everyone agree that this is what the average should be defined to be? So we are weighting this by the square, and that's basically because of the Born interpretation. Because Born said that the probability density is given by the mod squared of the wave function, right? So if that is the case, what is the expectation value of the position? Well, it will be given by minus infinity to plus infinity x times psi of x of t squared d of x divided by okay. So this is what we call the expectation value of the position, okay?
Is it like where on the wave I can expect the particle to be observed?
Yeah, we're on average, right? So yeah, and that's where basically if you essentially, you know, this as a statistical interpretation, suppose you have a particle, you have the wave function and you have multiple copies of it, right? You know, maybe many copies. It's called an ensemble, right? And then so you have the same copy of the state, and you do you measure its position. You measure its position, right? And then you find some probability, some distribution, and then you compute this average. Of course, you can only do it if you don't have the mathematical form of the wave function. You can only do it in a discrete fashion, but you know, we are not worried about those technicalities. And then you find where, on average, the particle is going to be. Okay. So now the next thing we have to ask is, how about the momentum? You know, what is the expectation value of P? So, and we can go to classical physics for inspiration. In classical physics, P is given by m times dx by dt. Okay, so you can say, okay, mass of a particle is, even in the quantum realm, it's a constant quantity. So we can say the expectation value of the momentum is going to be given by m times d by dt, expectation value of x. Right? So this is something which is reasonable. And then you say, okay, what now? Let's, for the sake of okay, calculation, I'm just going to assume that my wave function has been normalized. Okay, we can always do that. If the wave function is not normalized, if this is, say, n, then we can replace our wave function by psi divided by square root of n, and that new wave function is going to be normalized. Okay, so now let me compute P according to this formula. So this will be m, and then there'll be d of x. And then inside, I'm going to have x times the derivative operator is, you know, I can, because I'm integrating overall space, I can replace it by the partial derivative. But this consists of psi and psi star. So I can, by using Leibniz rule, I'll have two terms, one which would be the time derivative of psi, another term which would be the time derivative of psi star. And then we can use Schrodinger's equation and then replace those by the space derivative, and see that the potential terms will cancel because of the I. So we will have, as a result, 2m dx x times the real part, and I'm skipping a couple of steps here, psi star of I h bar by 2m d squared psi dx squared. Okay, so I've used Schrodinger equation going from this step to this step. Okay, so right.
Sir, is psi a modulus square is equivalent to position?
No, modulus squared, it's a probability density, right?
So partial differentiation of T of probability density. So
No, you
it was
don't.
replaced.
Yeah, just, okay, let me just do this. Okay, so, okay. So we want to do, we want to compute this, right? So this is psi star psi, right? So this is del psi star del t times psi plus psi star del psi by del t. Okay? Now, according to the Schrodinger equation, what do I have? I h bar d by dt of psi is minus h squared by 2m del squared psi del x squared plus v of psi, right? So that means that del psi by del t is equal to 1 over I h bar divided by minus h squared by 2m del squared psi del x squared plus v of psi. So then I can take its complex conjugate. Then on the right-hand side, I get minus 1 over minus I h bar. And here I get h squared by 2m del squared psi star del x squared plus v psi star, right? And then see that here, this is being multiplied by psi. So I multiplied this by psi. So here I have psi. And here, this is being multiplied by psi star. So I multiply this by psi star. And then I have psi star, okay? And these two terms have to be added. So if I add these two terms, the left-hand side is del by del t of psi star. And on the right-hand side, we see that there's a sign difference in this term and this term because of this minus I, right? And these two terms are the same. So this term will cancel this term. However, in this term, this is being, the derivative is on psi, and here the derivative is on psi star. So these two terms are not going to cancel, right? So these two terms are going to basically give me 1 over I h bar minus h squared by 2m. And then I will have del squared psi del x squared psi star. And then here's a minus sign, so I'm going to have minus del squared psi star del x squared psi. Okay? And here I can cancel one of the h's. Okay? And then I have I can take the I upstairs and that'll cancel this minus sign. So I get I h bar divided by 2m. And here we have a number minus its complex conjugate. When we have a number minus its complex conjugate, we have twice the real part, right? So we have t 2 times the real part of del squared of psi del x squared psi star. Okay, and then we have right? So this is basically what we get. Okay, so
স্যার কমপ্লেক্স কনজুগেট বিয়োগ করলে তো 2 টাইমস ইমাজিনারি পার্ট হয় না, মানে ওইদিকে মেবি প্লাস হতো।
Hang on. You're right. You're right. Right. Yeah. Mm,
আমরা নেগেটিভ এইচ বার স্কোয়ার বাই 2m কমন নিলে ওখানে প্লাস হয়ে যাবে না?
yeah. Okay. There's a minus sign, right? And so a plus ib minus. You're right. So this should be imaginary part, right?
Yes, sir.
And there should be a. Yeah, you're right. Yes. Yeah. So I guess, my notes, I have something slightly different, where essentially, I'm adding these two things, and it's basically twice the real of this guy, right?
Sir, ক্যালকুলেশনটা আবার করে দেখতে হবে।
I think so too. Let's see. IH bar. Okay, so this I'm sure this is basically the only minus sign, and so if I am adding these two things, so I 1 over h bar minus square blah blah. Okay, yeah, this is imaginary. Yeah, that's fine. So 2 times there's an I here, right? And so then we have minus h over m, imaginary part of del squared psi del x squared psi star. Okay, so the expectation value of p is going to be integral over d of x times x, and then minus h by m, imaginary part of this guy. Right. Okay. So now what I'm going to do is that I'm going to do an integration by parts. Okay. So there's minus h by m. And then here I'm going to do an integration by parts. If I do an integration by parts, what will happen is that, there'll be a total derivative term. So I have in my notes, I did it slightly differently, and let's try to see if we can do that and then generalize that, okay? So let's do it for it should be, it should be the same, but, let's consider a real particle, okay? Sorry, a free particle. Although the v terms do not, the v term doesn't. So if p is m dx of x d psi star of dt of psi plus psi star of d psi by dt. Okay, so this means that d of x is this thing is 2 times the real part of psi star d psi by dt. Okay. And, I think this should be generalizable to also the one with the v, but, let's just go with this, okay? So now, if I use a Schrodinger equation, if I use the Schrodinger equation, then this becomes 2m d of x, the real part of psi star. What should I get here? I should get here I h bar by 2m del squared psi del x squared. Okay, so this then can be written as, so this 2m will cancel this 2m, and I can write this as dx, the real part of I h bar x times, oh yeah, now I understand what I did wrong when I did the integration by parts. I forgot x. That's what I did wrong. Yeah, now I understand where I went wrong in the integration by parts. So here we have x and then times psi star d squared of psi dx squared. Okay? And then what we can do now, we can do an integration by parts, and because of this x, it'll generate one extra term. So when we do the integration by parts, and let's just take the real here and say I of h bar, we have, say, we have d by dx, and we have x psi star d psi by dx. And this term, because psi will, go to infinity, go to zero rapidly enough at infinity, much faster than anything we can imagine, this term will drop out. And then this thing, will be, it will be applied on this guy, and when it is acting on this guy, the x will vanish and we'll be left with psi star del psi by del x. Yeah. And then this guy will act on this guy. Well, okay, that, we have already taken care of that, right? So it'll act on this guy. So we have minus del psi star, and there'll be an x here, del x, del psi, del x. So yeah, I think I now understand what the problem was. And the problem was that when we did the integration by parts, so yeah, we can actually go back and fix our calculation. I forgot to take the derivative of this guy, so this guy was missing. So you see there's an I here, and there's a real here, and this is a real term. So this is not going to contribute. Okay? And this term is, you can show it's real. Okay? I times this term is real. So we can just write this as, and to show that, you just have to do integration by parts. Okay? So for example, I have I h bar, say there's a minus sign, and then star of d psi by dx, right? So if I take its complex conjugate, I have the I becomes minus I, so we have I of h bar, so there's a dx here, and then psi star becomes psi, and this becomes d psi star of dx, right? Now if I do an integration by parts, what will happen is that I'll have a term like this, which is psi star of dx, and this term is going to be vanishing because at infinity, these guys vanish, and then I will have a term which is minus I h bar of d of psi d of x times psi star of d of x, right? Which is, so if I look at this thing, this is exactly the same thing as with this minus sign. So we see that this term with this I is actually real. So this is, this vanishes. So we are left with only one term, and that term is, so then P is going to be given by minus infinity to plus infinity. psi star h bar by I del by del x by psi of d of x. Okay, so this is the expectation value of p. Okay, if we had not normalized psi, then the expectation value of p would be given by minus infinity to plus infinity psi star h bar by I d of psi d of x divided by psi star of psi of d of x. Okay, so you see now where I made the mistake. I made the mistake in forgetting when I did the integration by parts, there would be another term coming from the fact that we have an x here. Okay, and that term will be real. Well, so we had imaginary here, right, before we did the corrections. So that term would be real. So of course this term will not contribute, but that term will be, sorry, that term would be, that term will have an I, and if you do it carefully, I think you'll find that we will have this expression. Okay, so it doesn't matter if there's a potential energy or not. Okay, so what we can say is that for position, we see that we have to include in our expectation value in the integral x. But for momentum, we find that the object that we have to include in our integral is h over I del by del x. Okay,